Every mission to Mars you have ever imagined ends the same way. The astronauts land, plant a flag, collect their samples, climb back into their spacecraft, and fly home. It is the most natural assumption in the world. Humans go somewhere dangerous and humans come back. That is what exploration means. But a Mars mission is not an expedition to Antarctica or a voyage to the moon. The distance alone changes everything. And when you trace the full chain of what a return from Mars actually demands, from fuel that does not exist yet, to launch windows that open once every 26 months, to bodies that may be falling apart by the time the crew is ready to leave, the conclusion is terrifying. Getting to Mars may be the easy part. Coming home may be the part that breaks. If this is the kind of deep science storytelling you want more of, hit like and subscribe. It helps more than you think, and we have so much more to uncover together. Are you comfortable? Now, let's begin. Close your eyes for a moment and picture a Mars mission, not the technical version, not the version that lives in engineering papers and mission architecture documents. Picture the one you have carried in your head since you were a child. A rocket launches from Earth. Astronauts float through deep space for a few months, maybe watching the blue dot shrink behind them. They arrive at Mars. They land in a cloud of rust-colored dust. They step out. They plant a flag, collect rocks, take photographs that become the most famous images in human history. And then, after some dramatic period of survival and discovery on the surface, they climb back into their vehicle. They launch off Mars. They fly home. They splash down in the ocean. The world celebrates. Humanity has done it. That image lives in the mind of almost every person alive. It has been painted by artists, animated in documentaries, dramatized in Hollywood films, and sketched on whiteboards at NASA for over half a century. And in every single version of it, the ending is the same. The crew comes home. There is a reason this assumption feels so natural. It is built on everything we know about human exploration. Every expedition that matters in the public memory has a departure and a return. Columbus sailed west and came back east. The Apollo astronauts flew to the moon and splashed down in the Pacific. Even the International Space Station, humanity's longest continuous presence in space, operates on a rotation cycle. Crews go up, crews come down. The pattern is so deeply embedded that it does not feel like an assumption at all. It feels like the definition of the word mission. You go somewhere, you come back. But Mars is not the moon. It is not low Earth orbit. It is not any destination that human beings have ever traveled to, and the differences between Mars and every previous target of human spaceflight are not differences of degree. They are differences of kind. The gap between what Mars requires and what humanity has actually demonstrated in crude space exploration is so wide that it changes the fundamental nature of what a mission means. And nowhere is that gap wider, more dangerous, or more poorly understood by the public than in the part of the mission that everyone assumes is guaranteed: the return. To understand why the return is the problem, you have to first understand the shape of the mission itself. A human Mars mission is not a single event. It is a chain of events stretched across roughly 3 years, each link dependent on the one before it, and the final links are the most fragile of all. The most commonly studied architecture is called a conjunction class mission. It is the version that uses the least energy and therefore the least fuel, and it has been the baseline for almost every serious Mars mission study conducted by NASA, the European Space Agency, and independent researchers for decades. Here is how it works. Earth and Mars orbit the same star, but at different speeds and different distances. Earth completes one orbit roughly every 365 days. Mars takes about 687 Earth days. Because of this difference, the two planets align in a favorable geometry for efficient travel only once every 26 months, roughly every 2 years and 2 months. This alignment is called a launch window, and it dictates everything. When the window opens, you launch. The spacecraft follows what is called a Hohmann transfer orbit, an elliptical path that arcs outward from Earth's orbit to intersect with Mars's orbit. That transit takes between 7 and 9 months, depending on the specific alignment. On some windows, the geometry is more favorable than others, with the energy requirements varying on a roughly 15-year cycle tied to the eccentricity of Mars's orbit. Once the crew arrives at Mars and lands on the surface, they cannot simply turn around and fly home. The planets have moved. Earth is no longer where it was when they left. To return on an efficient trajectory, the crew must wait for the next favorable alignment. That wait is approximately 500 Earth days, roughly 16 months on the surface of Mars before the geometry of the solar system permits a return launch. Then the return transit begins. Another 7 to 9 months crossing deep space to reach Earth. Add it all together. 7 to 9 months outbound. Roughly 500 days on the surface. 7 to 9 months inbound. The total mission duration is approximately 900 days, nearly 2.5 years, sometimes closer to 3, depending on the specific window and the trajectory chosen. 900 days. Let that number settle. 900 days away from Earth. 900 days beyond the reach of any rescue vehicle, any emergency resupply, any hospital. 900 days during which every piece of hardware, every life support system, every calorie of food and liter of water and milligram of medicine must work or be repairable with only what the crew brought with them and what they can manufacture on a planet that is actively hostile to human life. For context, the longest single human spaceflight in history was cosmonaut Valery Polyakov's 437 days aboard the space station Mir, completed in 1995. That record still stands. It was achieved in low Earth orbit, roughly 250 miles above the surface, inside a vehicle that received regular resupply missions, that could communicate with the ground in near real time, and from which the crew could return to Earth in a matter of hours using an escape capsule if anything went seriously wrong. A Mars mission doubles Polyakov's record. It does so without resupply. It does so with communication delays that range from 4 minutes at the closest approach to over 22 minutes when the planets are on opposite sides of the Sun, meaning that a distress call from Mars would not even reach Earth for nearly half an hour, and the response would take another half hour to arrive. Round-trip communication of 44 minutes under worst-case geometry. No real-time conversation, no real-time guidance. No one on Earth can talk the crew through an emergency as it happens, and it does so with no abort capability. On every Apollo mission to the Moon, if something went wrong during transit, the crew could use the Moon's gravity to slingshot back toward Earth. The entire trip was measured in days. Apollo 13 suffered a catastrophic failure on the way to the Moon and still made it home in less than a week. On a Mars transit, if something fails 3 months into the outbound journey, the crew cannot turn around. They do not have the fuel. The orbital mechanics do not permit it. They must continue to Mars, land, survive, and hope the return chain still holds. The option to abort and come home early does not exist in any meaningful sense once the spacecraft has left Earth's gravitational neighborhood. This is the first and most fundamental difference between Mars and every crewed mission that has come before it. But conceivable. In low Earth orbit, rescue is routine. On Mars, rescue is not merely difficult. It is physically impossible with any technology that currently exists or is projected to exist in the next several decades. If something goes wrong on Mars, no one is coming. Let that reshape the image in your mind. This is not an expedition where a crew pushes into danger knowing that support is behind them. This is a crew that crosses a threshold beyond which they are entirely alone, and they stay alone for close to 3 years. To understand what that isolation actually means in operational terms, not just as a number but as a lived reality, Consider what happens when something goes wrong on the surface. An astronaut is outside the habitat, performing a routine equipment check during an extravehicular activity. A dust devil, one of the fast-spinning columns of thin Martian air that have been observed by rovers at heights exceeding 12 kilometers, sweeps through the work area and dislodges a component from the external power distribution panel. The panel sparks. A connection is severed. A warning alarm sounds inside the habitat. The crew member outside radios the situation to mission control and begins emergency assessment. And then they wait. The signal travels at the speed of light. Today, Mars is 18 light minutes from Earth. The crew member's report arrives at mission control 18 minutes after it was sent. The engineers on the ground hear a description of a situation that is already 18 minutes old. They confer. They analyze. They compose a response. They transmit. Their guidance arrives on Mars 18 minutes later. 36 minutes have passed since the crew member sent the initial report. More than half an hour in which the crew on Mars had no input, no guidance, no second opinion from the thousands of engineers who designed the systems they are trying to save. And the situation on Mars did not freeze while the signal traveled. It evolved. The power disruption cascaded into a secondary system. The crew member on the surface made a judgment call without ground support because they had no choice. By the time Earth's guidance arrives, it describes a scenario that no longer exists. The crew must adapt the advice to a situation that has moved beyond it, using their own judgment, their own training, and their own understanding of systems that are behaving in ways no ground simulation predicted, because no ground simulation included 16 months of Martian dust, thermal cycling, and radiation degradation. This is not an edge case. This is the operational reality of every emergency on Mars. The communication delay does not merely slow the response, it fundamentally changes the nature of the response. On the International Space Station, when an ammonia leak was detected in 2013, the crew and ground worked in real time, second by second, to isolate the leak and reconfigure the cooling system. That kind of collaborative crisis management is impossible on Mars. Every emergency is a solo performance. Every decision is made by a crew that is alone with the problem and alone with the consequences. Now consider what happens to the hardware during those 3 years. Every component of the mission system, the transit vehicle, the landing system, the surface habitat, the ascent vehicle, the life support equipment, the power generation systems, must survive and function across the entire mission duration. Not just during the dramatic moments, not just during the launch and the landing, during the boring months in between, during the 500 days on the surface when the crew is waiting for the planets to realign. Hardware does not age well in space. Cosmic radiation degrades electronics. Thermal cycling, the swing between extreme heat in sunlight and extreme cold in shadow, stresses materials and joints. Dust on Mars is not like dust on Earth. Martian dust is extremely fine, electrostatically charged, and pervasive. It infiltrated every system the Mars rovers encountered. Spirit and Opportunity dealt with dust accumulation that degraded solar panel performance. Curiosity's wheels showed significant wear from the abrasive Martian regolith. Now, imagine those same conditions acting on the systems that a human crew depends on to survive and to fly home. But the dust is not merely an abrasive nuisance, it is toxic. Martian regolith contains approximately 0.5% perchlorates, chlorine-based chemical salts that are harmful to human biology. Perchlorates damage the thyroid gland by interfering with iodine uptake, disrupt kidney function, and are broadly cytotoxic, meaning they damage human cells on contact. On Earth, perchlorate contamination in drinking water at levels measured in parts per billion triggers public health intervention. The Martian surface is coated in the substance. Every time an astronaut returns from a surface excursion, they bring dust back into the habitat. Every airlock cycle carries fine particles inward. Every piece of equipment moved between the exterior and interior transfers contaminated material. Spacesuits are not perfectly sealed against particles this fine. The Apollo astronauts on the Moon experienced significant irritation from lunar dust that entered the cabin after surface walks. Lunar dust is abrasive and irritating, but it is not chemically toxic. Martian dust is both. Over a surface stay of 500 days, involving dozens or hundreds of EVAs, the accumulation of perchlorate-laden dust inside the habitat is not a question of whether but how much. Air filtration systems can reduce airborne particle levels, but no system is perfect. Surfaces collect dust. Equipment collects dust. The crew breathes trace amounts, ingests trace amounts with food prepared in a contaminated environment, and absorbs trace amounts through skin contact. The effects are cumulative. Over 16 months, even low-level chronic perchlorate exposure could contribute to thyroid dysfunction, which in turn affects metabolism, energy levels, and cognitive function. It adds a chemical insult to the radiation, microgravity, and isolation stresses that are already degrading the crew. The surface of Mars is not just empty and airless. It is actively hostile at the chemical level, in a way that the Moon was not, and the crew must live in that chemistry for over a year before they even begin the return. The ascent vehicle, the rocket that must launch the crew off the surface of Mars and into orbit for the return trip, must sit on the Martian surface for the entire duration of the surface stay. That is over 500 days exposed to temperature swings that can range from roughly -80 degrees Fahrenheit at night to a relatively mild 20 degrees Fahrenheit during the day near the equator, only to plunge again after sunset. 500 days of fine abrasive dust working its way into seals, joints, and mechanisms. 500 days of radiation bombardment degrading sensitive electronics. 500 days during which that vehicle must remain not merely intact, but flight-ready. Ready to launch humans off the surface of another planet and execute a precision orbital maneuver with zero margin for error. No rocket in the history of spaceflight has been asked to do that. No rocket has sat idle on an alien surface for 16 months and then been expected to perform flawlessly on its first and only ignition. The vehicle has no test flight. There is no second attempt. If the ascent engine fails to ignite, or if the guidance system has been degraded by radiation, or if a seal has been compromised by thermal cycling, the crew is on Mars permanently. And this is where the comfortable assumption about return begins to crack. Because the public imagines the return as the mirror image of the arrival. You landed, so you take off. You flew here, so you fly back. But landing on Mars and launching from Mars are not symmetrical events. They are radically different in their engineering demands, and the launch is harder. Landing on Mars is itself an enormous challenge. Mars has an atmosphere, but it is thin, less than 1% of the density of Earth's atmosphere at sea level. That is thick enough to generate dangerous heat during entry, but too thin for parachutes to slow a heavy vehicle to a safe landing speed on their own. Every Mars lander to date has required a complex combination of heat shields, parachutes, and either retro-rockets or sky crane systems to reach the surface intact. And the heaviest object humanity has ever landed on Mars is the Perseverance rover, which weighed approximately 1,025 kilograms, roughly 1 metric ton. A crewed mission would need to land payloads tens of times heavier. The engineering challenge of landing large masses on Mars has been described by NASA engineers as one of the hardest unsolved problems in planetary exploration. But landing, as difficult as it is, benefits from one thing. It can be planned and executed from a position of relative strength. The crew and vehicle arrive at Mars with full fuel reserves for the landing maneuver, with systems that have been in transit for 7 to 9 months, but that were freshly assembled and tested on Earth before departure. The hardware is as close to factory new as it will ever be during the mission. Launching from Mars is the opposite. It happens at the end, It happens with hardware that has been sitting on Mars for over a year. It happens with fuel that, under current leading mission architectures, must be manufactured on Mars itself from Martian resources. It happens with a crew whose bodies have been degrading for over 2 years, and it happens with no margin. If it fails, there is no backup. This asymmetry between arrival and departure is the central structural problem of a Mars mission, and it is the thing that almost never appears in the public conversation. The romantic image of Mars exploration focuses entirely on the outbound leg, the launch, the transit, the approach, the landing, the first footsteps. Those are the moments that inspire. Those are the moments that dominate the concept art, the mission animations, the press conferences, and the cinematic dramatizations. The return is treated as an afterthought, as if coming home was simply the natural conclusion of a story that has already been told, as if the act of getting to Mars automatically implies the capability to get back. It does not. And the history of human spaceflight contains a warning that most people have forgotten. When President Kennedy committed the United States to landing a man on the moon in 1961, the engineering capability to do so did not exist. It had to be invented. And the part that nearly killed the program was not the launch from Earth, not the transit to the moon, not even the landing. It was the ascent from the lunar surface and the rendezvous in lunar orbit. The lunar module's ascent engine had to fire perfectly on the first attempt. There was no backup. If it failed, the astronauts on the surface were dead. NASA engineers called it the most critical single-point failure in the entire Apollo architecture. The engine worked. Every time, across 6 successful landings, it worked. But each ignition was a moment of absolute vulnerability. A single failure in a single component would have stranded 2 human beings on the moon with no possibility of rescue. And the moon is 3 days from Earth. Mars is 7 months from Earth. The ascent from Mars is the Apollo ascent engine problem, magnified by every dimension imaginable. Greater distance, greater duration, greater exposure, greater degradation, greater dependence on unproven systems, and absolutely zero possibility of a rescue mission arriving in time to matter. There is another dimension of this problem that rarely enters public discussion, and it concerns the basic shape of the solar system. The launch window constraint does not merely create an inconvenient wait time. It creates a hard boundary that transforms every problem on the surface into a potentially mission-ending delay. Consider this scenario. The crew lands on Mars. The fuel production system begins operating, converting Martian carbon dioxide and subsurface water ice into liquid methane and liquid oxygen for the return vehicle. The process is designed to take the full duration of the surface stay, roughly 500 days, to produce the required propellant load. Now imagine that 300 days into the surface stay, the fuel production system suffers a significant malfunction. A critical component fails. The crew can repair it, but the repair takes 60 days because replacement parts must be fabricated from limited onboard supplies. The fuel production system comes back online, but it is now 60 days behind schedule. The propellant load will not be complete by the planned launch date. The launch window does not care. Orbital mechanics is not negotiable. The planets move on their schedules, not on yours. If the fuel is not ready when the window opens, the crew cannot launch. They must wait for the next window. 26 more months. Over 2 additional years on Mars. But the mission was designed for a surface stay of 500 days. The food was calculated for that duration. The medical supplies were calculated for that duration. The life support consumables, the water recycling filters, the carbon dioxide scrubbers, all sized for 500 days with some margin. An additional 26 months roughly doubles the surface stay. The supplies were not designed for that. Picture what that extension looks like from inside the habitat. The science program is complete. The exploration objectives were finished months ago. The crew has nothing to do except maintain the systems, keeping them alive, and count the days until the next window opens. Food must be rationed, which means caloric intake drops, which means the physical decline already underway from radiation and reduced gravity accelerates. Water recycling filters designed for 500 days of use must now last over 1,200. Carbon dioxide scrubber cartridges must be stretched beyond their rated lifespan. Every consumable becomes a countdown. And the crew knows, with mathematical certainty, exactly how many days remain before each supply line runs dry, because they calculated those numbers the moment the window closed. They are not waiting with hope. They are waiting with arithmetic. And the arithmetic does not improve with time. It only gets worse. This is not a hypothetical edge case. This is the structural reality of Mars mission planning. Every delay on the surface risks cascading into a missed window, and a missed window does not just extend the timeline, it threatens the survival of the crew because the consumables cannot stretch to cover the gap. The margin between a successful return and a permanent stay is measured in days and weeks, not years. And the window constraint does not only apply to the departure from Mars, it applies to every phase of the return. The trans-Earth injection burn must happen within a specific range of dates. The trajectory must be calculated to arrive at Earth during a period when the entry angle is correct for atmospheric re-entry. Too steep and the vehicle burns up. Too shallow and it skips off the atmosphere and back into deep space with no fuel remaining to correct. The precision required is extraordinary, and it must be achieved by systems that have been operating in one of the harshest environments in the solar system for nearly 2 years. What you are beginning to see is that the return from Mars is not a single event, it is a chain, and every link in that chain must hold. Fuel production must succeed. The ascent vehicle must survive the surface stay. The launch must occur within the window. The orbital rendezvous must work. The trans-Earth injection must be precise. The transit vehicle's life support must sustain the crew for another 7 to 9 months. The Earth entry must hit the correct angle. The heat shield must perform after years of space exposure. The landing system must function. If any single link breaks, the chain fails. And unlike a chain on Earth, where you might find a workaround, jury-rig a repair, or call for help, this chain operates across millions of miles of vacuum with no external support. Every link is a single point of failure. Every failure is potentially permanent. This is the architecture of return. This is what the comfortable image of a Mars round trip actually requires. Not a dramatic, heroic effort concentrated in a few hours of white-knuckle intensity. A sustained, grinding, years-long sequence of systems operating correctly in an environment designed to break them, with a crew whose bodies are deteriorating and whose options narrow with every passing week. The public does not see this. The public sees the rocket launch and the first footstep. The public sees the flag and the photograph. The public sees the triumph of arrival and assumes the return is simply the arrival played in reverse. It is not. The arrival is the easiest part of the mission. It is the part where the hardware is newest, the crew is healthiest, and the systems are least degraded. Everything after landing is a countdown, not toward the triumphant return, but toward the moment when every accumulated weakness, every stressed system, every depleted resource, every degraded component must perform perfectly one final time. And that moment, the moment of return, is the most demanding, the most fragile, and the most assumption-dependent phase of the entire mission. The history of spaceflight is written in the stories of things that went right against extraordinary odds. Apollo 13, the Hubble repair mission, the miraculous survival of the crew aboard Mir during the 1997 collision. These stories create a narrative of human ingenuity overcoming mechanical failure, and that narrative is true. Humans are resourceful. Astronauts are extraordinary. Engineering teams on the ground can perform miracles of improvisation when they have real-time communication and a shared understanding of the vehicle. On Mars, none of those advantages apply. The crew is on their own. The ground team is 22 minutes away at worst. The vehicle has no spare parts beyond what was packed before launch, and the window is closing whether they are ready or not. This is the lie at the center of the Mars dream. Not a deliberate deception, but a failure of imagination. A failure to look past the landing and ask the harder question. The question that does not appear in the concept art or the press conferences or the inspirational speeches. Not, can we get there, but can we get back? And the answer, when you trace it through the engineering, the biology, the physics, and the mathematics, is far less certain than anyone wants to admit. What comes next is the chain itself, link by link, and the terrifying fragility hiding inside every connection. There is a number that governs every human Mars mission ever seriously proposed. It is not a speed, it is not a distance, it is a quantity of propellant, and it is so large that it reshapes the entire logic of the mission around itself. To launch a crew off the surface of Mars and send them on a trajectory back to Earth, the return vehicle needs propellant. Not a small amount. Not a modest tank of fuel, comparable to what a satellite carries, or what the Apollo lunar module burned during its brief ascent from the Moon. The quantities involved are staggering by any standard in the history of spaceflight. Under the most widely studied SpaceX Starship architecture, which as of the mid-2020s represents the most prominent crewed Mars concept under active development, the propellant requirement for the return flight is approximately 1,200 metric tons per vehicle. The baseline plan calls for 2 crewed Starships. That means the total propellant load that must be available on the surface of Mars before the crew can come home is roughly 2,400 metric tons of liquid methane and liquid oxygen. 2,400 metric tons. Produced not in a factory on Earth, not in a controlled industrial facility with decades of operational experience, but on the surface of another planet, by machines that have never been built at this scale, using resources that have never been extracted at this volume, in an environment where the average temperature hovers around -80 degrees Fahrenheit and the atmospheric pressure is less than 1% of what you are breathing right now. This is the return problem in its rawest form. You cannot bring the fuel from Earth. The mass penalty is prohibitive. Every kilogram launched from Earth's surface to Mars costs an extraordinary amount of energy, and stacking thousands of metric tons of propellant onto the outbound mission would require a launch campaign so vast and so expensive that it would dwarf anything in the history of human spaceflight by orders of magnitude. The math simply does not close. If you want to come home from Mars, you have to make your fuel there. But before you can make fuel, you have to land the machines that make it. And landing anything large on Mars is itself one of the hardest unsolved problems in planetary engineering. The engineering dead zone begins at entry. Mars's thin atmosphere generates lethal heating on any incoming vehicle, but cannot slow a heavy payload the way Earth's atmosphere does. No parachute system scales to the masses a crewed mission requires. At the surface, atmospheric pressure sits below 1% of sea level on Earth. A parachute that works perfectly in terrestrial conditions becomes nearly useless at these densities when the payload exceeds a few hundred kilograms. Every Mars lander to date has relied on a combination of heat shields, supersonic parachutes, and either retro-rockets or elaborate sky crane systems to reach the surface intact. And the heaviest object humanity has ever successfully landed on Mars is the Perseverance rover at approximately 1,025 kilograms, roughly 1 metric ton. A crewed Mars mission needs to land payloads in the range of 20 to over 100 metric tons. The ISRU propellant plant alone, with its processing equipment, power system, water extraction hardware, and cryogenic storage tanks would weigh many metric tons. The ascent vehicle is heavier still. A crewed starship, fully loaded, is designed for a landed mass far exceeding anything that has been attempted on any planetary body other than Earth. The problem is not simply scaling up existing landing technology. The physics changes at larger masses. At the speeds involved in Mars' atmospheric entry, a heavy vehicle generates enormous kinetic energy that must be dissipated before touchdown. Parachutes cannot be made large enough to slow these masses sufficiently in Mars's thin air. The leading solution is supersonic retropropulsion, firing the vehicle's engines against its direction of travel while still at supersonic speeds in the upper atmosphere to bleed off velocity before the final descent. SpaceX has demonstrated supersonic retropropulsion during Falcon 9 booster landings on Earth, where the atmosphere is thick enough to assist, and during early Starship test flights. But doing it on Mars, with a different atmosphere, different gravity, and a different thermal environment, is an untested maneuver. No vehicle has ever performed supersonic retropropulsion at Mars. The aerodynamic interactions between engine plumes and the thin Martian atmosphere at these scales are modeled but not validated. A failure during entry, descent, and landing does not damage the mission. It ends it. The crew, the habitat, the fuel plant, the ascent vehicle, all of it reaches the surface intact, or none of it matters. This entry and landing challenge sits upstream of everything else in the return chain. If you cannot land heavy payloads, you cannot deliver the ISRU plant. If you cannot deliver the ISRU plant, you cannot make fuel. If you cannot make fuel, you cannot come home. The very first link in the return chain is a technology that has never been demonstrated at the required scale. The concept of making fuel on Mars is called in-situ resource utilization, ISRU. It has been a cornerstone of Mars mission planning since the 1990s, when engineer Robert Zubrin popularized the Mars Direct architecture. The chemistry is well understood in principle. Mars has an atmosphere composed of roughly 95% carbon dioxide. If you can access water, either from subsurface ice deposits or from hydrated minerals in the regolith, you can split the water into hydrogen and oxygen through electrolysis. You then combine the hydrogen with carbon dioxide in a reaction called the Sabatier process to produce methane and water. The water gets recycled back into the electrolysis step. The methane becomes your fuel. The oxygen serves as your oxidizer and, conveniently, also as breathable air for the crew. On paper, it is elegant. Carbon dioxide is everywhere on Mars. Water ice exists in significant quantities beneath the surface at certain latitudes. The Sabatier reaction is well characterized. The individual chemical steps have been demonstrated in laboratories on Earth many times. There is no fundamental physics barrier preventing this from working. The problem is not the chemistry. The problem is the engineering. The problem is scale. And the problem is that before you even reach the engineering, you face a choice that may have no good answer. You have to decide where to land. ISRU requires water, large quantities of water. The total water requirement for producing the return propellant load has been estimated at well over 1,000 metric tons, not including the water needed for crew life support. The most accessible water on Mars exists as subsurface ice, confirmed by orbital radar and direct observation at higher latitudes, roughly above 45 degrees north or south. The Phoenix lander confirmed near-surface ice at 68 degrees north in 2008. Orbital data from Mars Odyssey and the Mars Reconnaissance Orbiter has mapped extensive ice deposits across the northern plains. But landing at high latitudes creates a cascade of additional problems. Solar energy diminishes as you move away from the equator. Temperatures are colder, increasing the energy needed to heat habitats and equipment. The seasonal variation is more extreme, with long periods of reduced sunlight during Martian winter. dust storm exposure patterns differ. And the landing terrain at high latitudes is often rougher and less well characterized than the equatorial plains where most successful landings have occurred. The equatorial regions offer better solar energy, more benign temperatures, and flatter terrain. But they have far less confirmed accessible water. Some equatorial sites show evidence of hydrated minerals or possible subsurface ice, but the quantities and accessibility are uncertain. Landing at the equator and discovering that the local water supply is insufficient or too deep to extract at the required rate means the ISRU plant cannot produce enough fuel. The return chain breaks at its foundation. This is not a trade-off that can be resolved from orbit. It requires ground truth. It requires robotic precursor missions that land at candidate sites, drill for water, measure extraction rates, and verify that the resource base can sustain industrial-scale propellant production over the required timeline. As of the mid-2020s, no such precursor mission has been funded, built, or flown. The site selection for the first human Mars mission, the choice that determines whether the crew can come home, will be made on the basis of orbital data and models rather than direct confirmation. The most significant real-world test of ISRU occurred aboard the Perseverance rover, which landed on Mars in February 2021, carrying an instrument called MOXIE, the Mars Oxygen in-situ resource utilization experiment. MOXIE was designed to demonstrate that oxygen could be produced from the Martian atmosphere using solid oxide electrolysis. It was roughly the size of a car battery. Over 16 operational runs between April 2021 and August 2023, MOXIE produced a total of 122 grams of oxygen. At its peak efficiency, it generated approximately 12 grams per hour at 98% purity or better, which was twice NASA's original performance goal for the instrument. MOXIE was a genuine success. It proved that the core electrochemical process works on Mars under real Martian conditions across a full Martian year of seasonal variation. That achievement matters. It moved ISRU from theoretical chemistry to demonstrated technology. But here is the scale problem in its starkest terms. MOXIE produced 122 grams of oxygen across its entire operational life. A full-scale system would need to produce tens of thousands of kilograms of oxygen, along with comparable quantities of methane. NASA has estimated that a human-rated oxygen production system would need to be roughly 200 times larger, approximately the size of a household washing machine, operating continuously for months, producing at least 2 kilograms of oxygen per hour with a dedicated power source generating 25 to 30 kilowatts, and oxygen is only half the equation. The methane production side requires water. Extracting water on Mars means either mining subsurface ice, which requires heavy excavation equipment and precise knowledge of where accessible deposits exist, or baking water out of hydrated regolith, which is energy-intensive and yields relatively small amounts per ton of material processed. Neither method has been demonstrated on Mars at any scale. Consider what scaling by a factor of 200 actually means. It is not simply building a bigger box. Every subsystem must be redesigned for continuous duty at industrial throughput. The compressor that draws in Martian atmosphere must handle vastly greater volumes. The electrolysis cells must be stacked into arrays that maintain uniform temperature and voltage across hundreds of individual units. The heat management system must dissipate thermal loads orders of magnitude larger than MOXIE produced. The control software must manage the integrated operation of water extraction, electrolysis, Sabatier reactors, gas separation, compression, and cryogenic liquefaction as a single coordinated process running without interruption for months. On Earth, scaling an industrial chemical process from laboratory prototype to production plant routinely takes a decade or more and involves building and testing multiple intermediate prototypes. On Mars, the prototype and the production plant must be the same machine. A peer-reviewed feasibility analysis published in Scientific Reports in 2024 examined the SpaceX Starship Mars mission architecture and identified the ISRU propellant production requirement as one of the most critical unresolved challenges. The authors noted that reliance on ISRU for the return flight mandates extraordinary reliability to avoid stranding the crew. A separate analysis published in early 2025 projected that developing and validating a full-scale Mars ISRU system would take at least 10 years, and far more likely 20, involving multiple robotic missions before any human crew could rely on it. Consider nuclear power as an analogy. The first nuclear chain reaction was demonstrated by Enrico Fermi in 1942 beneath the bleachers of a football stadium. The first commercial nuclear power plant did not begin operation until 1956, 14 years between proof of concept and operational deployment on Earth. With unlimited resources and industrial infrastructure, Mars ISRU faces all the same scaling challenges, plus the additional burden of operating autonomously on another planet across a communication delay that prevents real-time troubleshooting. And even if the propellant is produced, it must be stored. This is a problem that receives almost no public attention, but that engineers working on Mars mission architectures take very seriously. Liquid methane and liquid oxygen are cryogenic propellants. They must be kept at extremely low temperatures to remain in liquid form. Liquid oxygen boils at -297 degrees Fahrenheit. Liquid methane boils at -259 degrees Fahrenheit. On the Martian surface, ambient temperatures are cold, but not cold enough to maintain these cryogenic conditions passively. The propellants will warm and boil off unless actively refrigerated. Storing 2,400 metric tons of cryogenic propellant on the Martian surface for the duration of the production period, potentially a year or more, requires a refrigeration and insulation system of a scale that has never been deployed beyond Earth. Boil-off losses must be either prevented through continuous cooling or compensated through excess production. Either approach demands additional power, additional equipment, and additional time. A refrigeration failure that allows a significant fraction of the stored propellant to boil off could consume weeks or months of production margin, potentially pushing the fuel load below the threshold needed for return. The storage problem also interacts with the dust problem. Martian dust accumulating on storage tanks changes their thermal properties. Dust on radiator surfaces reduces cooling efficiency. Dust infiltrating mechanical systems degrades pump and valve performance. Every system sitting on the Martian surface for an extended period is engaged in a slow battle with the environment, and the environment does not take days off. And every one of these systems shares a single upstream dependency that the public conversation almost never examines. Power. The ISRU propellant plant needs 25 to 30 kilowatts just for oxygen production. Water extraction requires additional power for drilling and heating. Cryogenic refrigeration draws continuous power around the clock. The habitat needs power for life support, thermal regulation, lighting, communications, and medical systems. The total continuous power demand for a crewed Mars surface mission with active ISRU has been estimated in NASA architecture studies at roughly 40 to 100 kilowatts, depending on the design. Solar panels alone cannot reliably deliver this. Mars receives roughly 43% of the solar energy that Earth does, and dust accumulation degrades output over time. The baseline power source for any serious Mars surface architecture is nuclear fission. The most developed concept is kilopower, a small fission reactor using a uranium-235 core with Stirling engine converters. Each unit produces roughly 10 kilowatts of electrical power. A mission requiring 40 to 100 kilowatts would need 4 to 10 individual reactors operating simultaneously on the Martian surface. Each reactor must be landed intact. Each must be deployed at a safe standoff distance from the habitat, typically 100 meters or more, to protect the crew from neutron and gamma radiation during operation. That standoff distance means running power cables across the Martian surface, cables that must survive thermal cycling, abrasive dust, and potential physical damage for the full mission duration. The cables connect to a power distribution system that manages load balancing across multiple reactors and multiple consumers simultaneously. A surface electrical grid on another planet, built and maintained by a crew of 4 to 6 people with no external support. If one reactor fails, the power margin shrinks. The ISRU plant may need to reduce production. The refrigeration system may accept higher boil-off losses. These are manageable compromises as long as the remaining reactors hold. If 2 fail, the margin may disappear. The mission enters a mode where power allocation becomes a zero-sum competition between keeping the crew alive and producing the fuel that gets them home. Life support cannot be reduced. The ISRU plant cannot produce fuel without power. And stored propellant continues to boil off if the refrigeration system is depowered. No nuclear reactor of any kind has ever operated on the surface of Mars. The kilopower design was tested in a ground demonstration called Krusty, which ran for 28 hours at full power in a Nevada facility in 2018, 28 hours on Earth. The Mars mission requires years of continuous operation in conditions the test facility could not replicate. Power is the invisible foundation beneath the entire return chain. Without it, the ISRU plant stops, the propellant boils off, the habitat goes cold, and the life support fails. It is the quietest link in the chain and one of the most critical. And then there is the weather. Not weather in the human sense. Mars has no rain, no thunderstorms, no hurricanes. But it has something arguably worse for a surface mission dependent on a production timeline. Global dust storms. Mars experiences planet-encircling dust events roughly every 3 to 4 Mars years. These are not localized squalls. They are storms that begin in one region and within weeks engulf the entire planet in a shroud of fine dust so thick that the sky goes dark. During the 2018 global dust storm, atmospheric opacity increased by a factor of more than 10. The sun was reduced to a faint glow. Surface solar energy dropped to near zero. The Opportunity rover, which had survived on Mars for nearly 15 years, was killed by that storm. Its solar panels could not collect enough energy to keep its batteries charged through the weeks of darkness. A global dust storm during the surface stay of a human mission would be a multi-system crisis. If the ISRU propellant plant relies on any solar-augmented power, and most proposed architectures include at least supplementary solar panels alongside a nuclear reactor, production could drop sharply or halt entirely for the duration of the storm. Even a fully nuclear-powered plant would be affected. Outdoor operations cease during a global storm. No EVAs, no equipment maintenance, no water mining if the extraction site is external to the habitat. Thermal management systems must work harder as dust coats surfaces and changes heat exchange dynamics. Visibility drops to near zero, and the storm can last months. The probability of a global dust storm occurring during any given 500-day surface stay is not negligible. If it occurs early in the stay, the production timeline absorbs the hit and may recover. If it occurs late, during the final months before the launch window opens, the consequence could be a propellant shortfall that no amount of post-storm acceleration can recover. The window does not wait for the dust to settle. At this point, a careful listener might ask a reasonable question. Why not use faster propulsion to shorten the trip and reduce these risks? The short answer is that faster propulsion helps, but does not solve the return problem, because the return problem is not primarily about speed. Nuclear thermal propulsion could reduce transit times from 7 to 9 months down to perhaps 4 to 6 months. That is a meaningful reduction in radiation exposure and microgravity time. But the crew still must land on Mars, produce fuel using ISRU, survive the surface stay, launch from Mars on an ascent vehicle that has sat for over a year, and execute the full return chain. The surface stay is governed by orbital mechanics, regardless of engine type, and the launch window constraint remains a hard boundary. Nuclear electric propulsion offers different trajectory options, but cannot perform the high-thrust maneuvers needed for orbit insertion, descent, or ascent. Chemical or nuclear thermal engines are still required for those phases. The ISRU dependency remains. The surface stay risk remains. Faster propulsion is an improvement at the margins of a problem whose core is structural. The return from Mars is hard, not because the transit is slow, but because the entire chain depends on systems that must function after years of exposure and a crew that must perform after years of degradation. Shortening the transit by a few months does not change the fundamental character of that challenge. Now, layer on the timeline constraint. Under current mission architectures, the ISRU system does not arrive with the crew. It must be sent ahead on a prior launch window, landed on Mars, and brought to operational status before the human mission launches from Earth. The crew does not depart until ground controllers have confirmed that the propellant production system is functioning and that sufficient fuel will be available for the return. If the system fails during this pre-deployment phase, the crewed mission does not launch. That is the optimistic scenario. The nightmare scenario is one where the system appears to be functioning correctly during pre-deployment. The crew launches from Earth and arrives on Mars, and then the ISRU system fails during the surface stay. Perhaps a critical seal degrades. Perhaps the water extraction encounters unexpected geology. Perhaps the power supply develops a fault that reduces output. In any of these cases, the crew is on Mars with a vehicle that cannot fly. The next resupply window is 26 months away. Even if a replacement could be launched immediately, it would not arrive for roughly 9 months after the window opened. The crew would be waiting nearly 3 years for a fix, assuming one could even be delivered and assuming their supplies lasted. This is the tyranny of the window. It is not merely an inconvenience. It is a structural feature of the solar system that converts every equipment failure into a potential survival crisis. On the International Space Station, if a critical system fails, a resupply vehicle can reach the station within days to weeks. In an extreme emergency, the crew can evacuate to Earth within hours. On Mars, the safety net does not exist. Let us now trace the full return sequence, step by step. Step 1. Propellant production. The ISRU system must have produced and stored the full propellant load. This means not just producing the methane and oxygen, but liquefying them and maintaining them in cryogenic storage while managing boil-off. Any shortfall means insufficient delta V for the return trajectory. Step 2. Ascent vehicle readiness. The rocket must be fully fueled, structurally sound, and operationally verified after sitting on Mars for over 500 days. Every valve, pump, actuator, sensor, wire, and seal must function correctly on the first attempt. There are no technicians on Mars. The crew themselves must conduct final checkouts using whatever diagnostic tools they have, interpreting data from systems exposed to conditions no Earth-based qualification program can fully simulate. Step 3. Launch. The ascent vehicle must ignite and lift off. Mars has lower gravity than Earth, roughly 38%, but its thin atmosphere provides almost no aerodynamic lift. The vehicle relies entirely on thrust. The ascent must achieve a precise Mars orbit, matching the trajectory parameters required for the next step. Step 4. Orbital operations. The crew may need to rendezvous and dock with an orbiting transfer vehicle that has been waiting in Mars orbit for over 2 years, exposed to radiation, thermal cycling, and micrometeorite flux. The docking must succeed. Systems must be verified. Life support must be reactivated. Step 5. Trans-Earth injection. The transfer vehicle must fire its engines at the correct time, direction, and duration to intercept Earth's orbit. The timing is dictated by orbital mechanics and is not flexible. If the burn is delayed or the engine underperforms, the trajectory misses Earth. Step 6. Deep space transit. The crew must survive another 7 to 9 months. Life support that has been operating for over 2 years must continue functioning. Food and medical supplies must be sufficient. Step 7. Earth entry. The vehicle must hit a precision entry corridor. A few degrees too steep, and the deceleration forces are lethal. A few degrees too shallow, and the vehicle skips off the atmosphere into an unrecoverable orbit. The heat shield must perform after years of exposure. Step 8. Landing and recovery. 8 steps, each dependent on the one before it, each involving systems that have been in operation for years, each a potential single point of failure. As of the mid-2020s, humanity has never launched a vehicle from the surface of another planet. Not once. Not even robotically. The Mars Sample Return mission, which would have been the first demonstration of launching a rocket from Mars, saw its funding effectively eliminated by Congress in January 2026. That cancellation means the first time a rocket launches from Mars, if current plans hold, it will be carrying human beings. No orbital test. No robotic test. No subscale demonstration. The risk tolerance implied by this sequence is extraordinary. In conventional aerospace engineering, major systems undergo years of ground testing, uncrewed flight testing, and incremental crewed testing. A Mars return mission under current timelines would skip several of these stages. The ISRU system would be tested at scale for the first time on Mars. The ascent vehicle would fly for the first time from Mars. The entire return chain would be executed for the first time with a crew aboard, from a planet where failure means no rescue. There is a concept in engineering called system reliability. For a chain of components in series, the overall reliability is the product of the individual reliabilities. 10 components at 99% each give roughly 90% system reliability. 50 such components give about 60%. 100 give roughly 37%. A Mars return chain involves not 100 components, but thousands, many never tested in the operational environment. Even with extremely high individual reliability, the sheer number of systems that must function in sequence drives the overall probability of success below what any space agency has historically accepted for crewed missions. This does not mean return is impossible. It means that return is the part of the mission where uncertainty concentrates, where assumptions stack highest and margins are thinnest, where the consequences of being wrong are most absolute. And here is the dimension that makes all of this worse. Everything described so far assumes the hardware performs as designed. It assumes the systems work. But the crew is not hardware. The crew is human. And by the time they need to execute the return, their bodies will have been through something no human being has ever experienced. What comes next is what happens to a human body across 900 days beyond the protection of Earth, and why the biological clock may be the most unforgiving constraint of all. Everything we have discussed so far describes machines, rockets, reactors, propellant plants, guidance computers, heat shields, systems built by human hands and subject to human engineering analysis. Systems that can be modeled, tested, redesigned, and improved. Systems that degrade in predictable ways and that can, in theory, be made robust enough to survive the conditions Mars imposes. But there is one system in the mission chain that cannot be redesigned. It cannot be swapped out for a more durable version. It cannot be radiation hardened or thermally insulated or sealed against dust. It was built by biology, not by engineers, and it was never meant to operate in the environment a Mars mission demands. The human body. A crew departing Earth for Mars carries everything they need to survive the transit inside their spacecraft and inside their own skin. The spacecraft can be repaired, the skin cannot. And over the course of a mission lasting approximately 900 days, the cumulative damage inflicted on the human body by radiation, microgravity, isolation, and the sheer duration of the exposure builds in ways that no previous spaceflight mission has tested. By the time the crew is ready to execute the return, the most vulnerable component in the entire chain is not the ascent vehicle or the fuel plant. It is the crew themselves. Start with radiation. It is the risk that most people have heard of, and the one that almost no one fully grasps in the context of a Mars mission. On Earth, you are shielded by two layers of protection. The first is Earth's magnetosphere, the invisible bubble of magnetic force generated by the planet's liquid iron core. The magnetosphere deflects the vast majority of charged particles streaming from the sun and from deep space. The second is the atmosphere itself. Roughly 100 kilometers of gas above your head absorbs most of what gets through the magnetic field. Together, these shields reduce your annual radiation dose to a few millisieverts. In deep space, both shields are gone. Astronauts aboard the International Space Station receive some residual protection from the magnetosphere. Even so, a typical 6-month ISS mission exposes an astronaut to roughly 80 to 160 millisieverts, depending on solar activity. A Mars mission is different in kind. Once the spacecraft leaves Earth's magnetosphere, the crew is exposed to the full deep space radiation environment for the duration of the transit, both outbound and inbound. That environment is dominated by two sources. The first is galactic cosmic radiation. These are high-energy particles, primarily protons but also heavier nuclei up to iron and beyond, accelerated to enormous speeds by supernova explosions across the galaxy. They arrive from all directions, continuously, and they carry enough energy to penetrate spacecraft walls and human tissue. Some are so energetic that no practical amount of shielding can stop them. A researcher at the University of Washington described them in terms that are difficult to forget. They rip through you like you are cellophane. The second source is solar particle events, sudden bursts of high-energy protons emitted during solar flares and coronal mass ejections. These are episodic and unpredictable. During the September 2017 solar storm, radiation levels on the surface of Mars temporarily doubled. If a crew had been in transit during an event of that magnitude without adequate storm shelter shielding, the acute dose could have caused immediate radiation sickness. The most reliable measurement of the deep space radiation dose comes from the RAD instrument aboard the Mars Science Laboratory spacecraft that delivered Curiosity in 2011 and 2012. The result was 0.66 sieverts for the round trip, transit only. Adding surface exposure over 500 days, a Mars crew would receive a total mission dose approaching or exceeding 1 sievert. NASA's risk models have predicted that radiation-induced mortality and morbidity from a Mars mission could exceed 5% and 10% respectively, with upper confidence bounds reaching significantly higher. Cancer risk has traditionally been the dominant concern, but recent research has expanded the picture. Radiation exposure in deep space has been linked to cardiovascular disease, cataracts, central nervous system effects, including potential cognitive decline and degenerative tissue damage. The heavier nuclei in galactic cosmic radiation create dense tracks of ionization through tissue, breaking DNA strands in clustered patterns that the body's repair mechanisms struggle to fix accurately. And then there are the kidneys. In 2024, a landmark study led by researchers at University College London and involving more than 40 institutions across 5 continents, produced the most comprehensive analysis of kidney health in spaceflight ever conducted. Published in Nature Communications, the study examined data from over 40 low Earth orbit missions and 11 ground-based simulations. Several simulations exposed mice to doses of galactic cosmic radiation equivalent to Mars mission durations. The findings were alarming. Kidney tubules responsible for regulating calcium and salt balance began shrinking after less than a month in space. Spaceflight fundamentally alters how kidneys process salt, likely contributing directly to the elevated rate of kidney stone formation in astronauts. But the most devastating result came from mice exposed to simulated galactic cosmic radiation for 2.5 years. Their kidneys suffered permanent damage and loss of function. The lead author stated it plainly. While an astronaut could make it to Mars, they might need dialysis on the way back. Dialysis on a spacecraft, 7 months from Earth. With no hospital, no nephrology team, and no margin for the kind of medical emergency that kidney failure can produce. Now, add what microgravity does to the rest of the body. Bone loss. In the absence of gravitational loading, the human skeleton loses mineral density at roughly 1 to 1.5% per month in weight-bearing bones. An astronaut in microgravity loses in a single month what a person on Earth loses in 6 months to a year. Over a 9-month transit, cumulative loss can reach 10% or more. The surface of Mars provides partial relief. Martian gravity is roughly 38% of Earth's. But whether that is sufficient to halt or significantly slow bone loss is an open question. No human being has ever lived in partial gravity for an extended period. It has never been measured. It is an assumption built into every mission plan. If the assumption is wrong, a crew that spent 500 days on the surface could arrive at the return transit with skeletal systems significantly compromised, facing another 7 to 9 months of zero gravity, during which loss would accelerate. The cumulative deficit by Earth arrival could create a meaningful risk of fracture during the high G deceleration of atmospheric entry. A femur weakened by 2.5 years of mineral depletion must withstand loads it may no longer be capable of bearing. Countermeasures exist. ISS astronauts exercise approximately 2 hours per day. These protocols have reduced but not eliminated bone loss. Even with aggressive exercise, some astronauts return from 6-month missions with deficits that take years to recover, and some studies suggest full recovery may never occur in certain bones. Muscle atrophy follows a parallel trajectory. Without gravitational loading, skeletal muscles weaken and shrink. The muscles most affected are those maintaining posture and supporting locomotion. Over a mission of this duration, even with daily exercise, some degree of weakening is expected. Women are particularly susceptible due to lower baseline muscle mass and hormonal differences. Cardiovascular deconditioning accumulates alongside it. In microgravity, the heart does not work as hard against gravity. Over months, the heart muscle atrophies slightly, blood volume decreases, the body's ability to regulate blood pressure degrades. Many returning astronauts experience orthostatic intolerance, dizziness, fainting, and in severe cases, loss of consciousness upon re-entering a gravitational environment. And then there are the eyes. Spaceflight-associated neuroocular syndrome is one of the more recently recognized hazards. In microgravity, bodily fluids shift toward the head, increasing intracranial pressure, which can cause swelling of the optic nerve, flattening of the eyeball, and measurable changes in vision. More than half of astronauts on extended ISS missions have experienced some degree of visual impairment. Some changes have persisted after return to Earth. A crew member whose vision has degraded must still read instruments, operate controls, and execute precise manual tasks during the return sequence. The immune system adds another layer. Spaceflight suppresses immune function through mechanisms that are complex and not fully understood, involving changes in immune cell behavior, reactivation of latent viruses, and alterations in inflammatory response. An immunocompromised crew in a closed environment for nearly 3 years represents an epidemiological scenario with no terrestrial analog. Now consider a dimension of the Mars medical problem that almost never appears in the public discussion. What happens when a crew member has a medical emergency that requires surgical intervention? On the International Space Station, the medical kit includes basic supplies for wound care, minor procedures, and pharmacological management of common conditions. If an astronaut suffers a serious medical event, the standard protocol is emergency evacuation. Within hours, the patient can be in a capsule descending toward Earth and shortly after in a hospital operating room. On Mars, that protocol is meaningless. Over a 900-day mission with a crew of 4 to 6 people, the statistical probability of at least one serious medical event is not small. Appendicitis alone has a lifetime incidence of roughly 7 to 8%. For a crew of 6 over nearly 3 years, the probability that at least one crew member experiences acute appendicitis is meaningful. Kidney stones, as already discussed, are elevated by spaceflight conditions. Dental abscesses, bone fractures, especially given the skeletal weakening from microgravity, lacerations deep enough to require surgical repair, hernias from the physical exertion of surface operations in spacesuits, cardiac events, given the cardiovascular deconditioning. These are not exotic possibilities. They are the ordinary hazards of human existence compressed into an environment with no emergency room. The crew may include a physician, but one physician is not a surgical team. Performing an appendectomy in a spacecraft or a Mars surface habitat with limited imaging, limited anesthesia, no blood bank, no sterile operating theater, and no second opinion requires a level of autonomous medical capability that no space mission has ever carried. If the physician is the patient, the situation becomes even more stark. The remaining crew must manage a medical crisis with whatever training they received before departure, which is necessarily limited by the time available for cross-training. A crew member who is seriously ill or injured is not contributing to mission operations. They require care, which draws another crew member away from their duties. In a team of 4, losing one member to illness and one to caregiving reduces operational capacity by half. If the medical event occurs during a critical phase, during the ascent vehicle checkout, during the launch preparations, during the return transit, the mission's ability to execute complex procedures may be dangerously compromised. NASA has studied the problem extensively. Reports from the agency's Human Research Program have identified the absence of definitive medical care as one of the highest risk elements of a Mars mission. Some researchers have proposed autonomous surgical robots, but the communication delay makes real-time telesurgery impossible. Others have proposed training crew members in emergency procedures using simulators. These are partial solutions at best. The honest assessment is that a crew member who suffers a serious surgical emergency on Mars may not survive it, and even those who survive may be permanently impaired, and the medical supplies themselves are subject to the same degradation that affects every other system on the mission. Pharmaceuticals have shelf lives. Many common medications, including certain antibiotics, pain management drugs, and emergency cardiac medications, begin to lose potency after 1 to 2 years, even under optimal storage conditions. Radiation exposure accelerates pharmaceutical degradation. Research has found that the deep space radiation environment can alter the chemical structure of medications in ways that reduce effectiveness or in some cases produce harmful breakdown products. The medical kit that launches from Earth fully stocked and carefully curated will not be the same kit 2 years later when a medical emergency occurs. The antibiotics may be weaker. The pain medications may be less effective. The emergency drugs may have degraded below therapeutic thresholds. The crew will be managing medical crises with a pharmacy that is aging alongside them. Now add one more factor that interacts with every biological risk discussed so far: the food. A Mars mission cannot carry fresh produce. It cannot receive resupply. Every calorie the crew will consume must be packaged, preserved, and loaded before departure. The total food mass for a crew of 4 over 3 years is estimated at roughly 11,000 kilograms of pre-packaged meals that must remain edible and nutritionally adequate across the full mission duration. That is not just a logistics number. It is a constraint that shapes crew health, morale, and performance across the entire mission. The problem is that pre-packaged space food degrades over time. Vitamins break down. Vitamin C, thiamine, folic acid, and vitamin A are among the most susceptible. Studies by NASA's Food Science program have shown that after 3 to 5 years of storage, nutritional content declines measurably. The meals the crew eats during the return transit, 2.5 to 3 years after preparation, will contain less bioavailable nutrition than the same meals consumed at the start. The food also changes in taste and texture over time. Fats oxidize, flavors flatten, textures become less appealing. Research on long-duration confinement studies has shown that food monotony, the psychological effect of eating the same limited menu for months or years, produces measurable declines in caloric intake. Crew members simply eat less because the food becomes unpalatable through repetition. Reduced caloric intake in an environment that is already taxing the body through radiation, microgravity, and chronic stress accelerates muscle loss, weakens the immune response, and impairs wound healing. This nutritional decline interacts directly with the physical degradation already underway. A body losing bone density needs adequate calcium, vitamin D, and supporting micronutrients. A suppressed immune system needs vitamins C and E, zinc, and other nutrients. A deconditioned cardiovascular system needs proper caloric balance. The crew is being asked to endure the most demanding phase of the mission while eating food at its lowest nutritional value. The body repairs damage with progressively worse fuel. NASA has identified food system stability as a critical technology gap and has funded research into improving shelf life. None of these solutions are mature enough for operational deployment. There is one more biological stressor that is unique to the Martian surface, and that compounds every other effect discussed so far: the Martian day. A sol, the term for a Martian day, is 24 hours and roughly 39 minutes long. That is close enough to an Earth day to seem trivial. It is not. The human circadian rhythm, the internal clock that regulates sleep, hormone release, metabolism, cognitive performance, and immune function, evolved over millions of years to synchronize with a 24-hour light-dark cycle. It is one of the most deeply embedded biological programs in the human body. Sleep science has demonstrated that even small chronic mismatches between the environmental cycle and the internal clock produce measurable effects when sustained. A consistent 39-minute daily drift might sound negligible, but over weeks and months, the body's attempts to synchronize with the Martian light cycle, while its internal clock insists on a 24-hour rhythm, create a state of perpetual low-grade circadian disruption. The effects are well documented: degraded sleep quality, increased daytime fatigue, reduced cognitive sharpness, impaired memory consolidation, altered hormone profiles, including cortisol, melatonin, and growth hormone. NASA learned this firsthand during the early phases of the Mars rover missions. Operations teams at the Jet Propulsion Laboratory were asked to live on Mars time during the initial weeks of the Spirit and Opportunity missions, shifting their schedules by roughly 40 minutes each day to stay synchronized with the rover's work cycles. Within weeks, team members reported significant fatigue, disorientation, sleep disruption, and reduced performance. The practice was eventually abandoned because it was unsustainable. And those were people living on Earth, in their own homes, with full access to food, medicine, daylight, and rest. They were merely shifting their clocks. A crew on Mars would be immersed in the Martian light cycle for over 500 days. They would experience Martian dawn and Martian dusk through habitat windows. Their work schedules would be tied to surface operations conducted during Martian daylight. Their bodies would fight the 39-minute drift every single sol for 16 months. The cumulative cognitive and physiological cost of this chronic circadian misalignment layers on top of the radiation damage, the bone loss, the muscle atrophy, the cardiovascular deconditioning, and the immune suppression. It makes every other problem slightly worse, every day, for the entire surface stay. Now, step back and consider the composite picture. A crew member approaching the end of the surface stay on Mars is not the same person who launched from Earth 2 years earlier. They have accumulated a radiation dose approaching or exceeding career limits. Their bones are weaker, their muscles are diminished, their cardiovascular system is deconditioned, their vision may be impaired, their kidneys may be structurally altered, their immune system is suppressed. The food sustaining them is nutritionally degraded. They have been chronically sleep disrupted by a day length their body cannot fully adapt to. They face a non-trivial probability of a medical emergency for which no adequate treatment exists. They have been living in a confined space with a small group of people, cut off from everyone they know, for longer than any human being in history. And this is the person who must now execute the most demanding phase of the entire mission, the return. The psychological dimension compounds everything. The communication delay with Earth, 4 to 22 minutes one way, means the crew cannot have a real-time conversation with mission control. For periods lasting roughly 2 weeks, when Mars passes behind the Sun, communication is blocked entirely. During those blackout windows, the crew is truly alone. Studies of isolated environments on Earth, including Antarctic winter overmissions, submarine deployments, and dedicated analogues such as the Mars 500 experiment conducted in Moscow between 2010 and 2011, have documented sleep disruption, interpersonal conflict, motivational decline, cognitive slowing, and symptoms consistent with depression and anxiety. The Mars 500 experiment confined 6 volunteers for 520 days. Crew members experienced significant disruptions to sleep-wake cycles. Physical activity declined. At least one showed signs of chronic sleep deprivation and reduced engagement during later phases. And that was a simulation. The participants knew they were in Moscow. The psychological weight of a real Mars mission would be categorically heavier. Compound the psychological burden with physical degradation. A person who is sleep-deprived, physically weakened, and in chronic low-grade pain from musculoskeletal deconditioning does not make decisions well. They are slower to recognize problems, more susceptible to errors, and less capable of sustaining focused attention. The return sequence demands precisely the kind of high-performance decision-making that extended spaceflight degrades. And the return transit itself is not merely a repetition of the outbound journey in better-known conditions. It may be the single most dangerous period for the crew's health. When the crew launches from Mars and re-enters zero gravity for the return, they are not starting from the baseline they had when they left Earth. They are starting from a body that has spent 500 days partially adapted to Martian gravity. That partial adaptation means their cardiovascular system, their musculoskeletal system, and their fluid balance have reached some intermediate state between Earth normal and the zero-gravity deconditioning of the outbound trip. When they re-enter microgravity for the return transit, a new wave of adaptation begins. Fluids shift headward again. Bone loss accelerates again. Cardiovascular deconditioning resumes from a lower baseline than the outbound starting point. The crew enters this second zero-gravity phase in far worse condition than the first. They are also eating food that is now 2.5 years old. The nutritional degradation that was a concern during the surface stay is more pronounced during the return transit. The vitamins that support bone maintenance, immune function, and tissue repair are at their lowest levels precisely when the body needs them most. And the psychological landscape of the return transit carries its own distinct burden. Research on long-duration isolation consistently identifies a pattern, sometimes called the third quarter phenomenon. During the middle and later portions of a confinement period, after the initial novelty has worn off and the end is visible but not yet reached, crew members frequently experience a characteristic cluster of symptoms. Irritability increases. Social withdrawal becomes more common. Motivation drops. Small conflicts that were managed earlier in the mission become harder to contain. Sleep becomes more disrupted. The sense of meaninglessness, of time stretching without purpose, settles in. The return transit is the third quarter of the Mars mission. The excitement of landing and surface exploration is behind them. The monotony of transit stretches ahead. The anxiety of Earth entry looms. And the crew knows that they are still 7 to 9 months from home, in a vehicle that is older than it has ever been, with bodies that are weaker than they have ever been, eating food that is worse than it has ever been. If 2 crew members experience serious medical events simultaneously during this phase, and over a 3-year timeline, that possibility is a statistical reality rather than a remote edge case. The mission's ability to execute the precision maneuvers required for Earth entry may be critically compromised. And when Earth entry finally arrives, the crew must endure deceleration forces that would be challenging for a healthy person and may be dangerous for a body in their condition. Atmospheric re-entry from a Mars return trajectory involves speeds higher than those experienced by crews returning from the Moon. The vehicle will hit the upper atmosphere at roughly 12 to 14 kilometers per second. The deceleration will compress the crew into their seats at multiple times Earth gravity. Bones that have lost density for nearly 3 years must absorb those loads. A cardiovascular system that has been deconditioned by microgravity must maintain blood pressure under sudden gravitational stress. Muscles that have atrophied must stabilize the body and the head against the G-forces. An astronaut who loses consciousness during re-entry cannot respond to contingencies, cannot monitor instruments, cannot take manual control if automated systems fail. The margin between a controlled landing and a fatal one may depend on whether the crew's bodies can tolerate the final minutes of a 3-year journey. The biological clock runs in one direction. It does not pause. It does not reset. Every day on Mars, every day in transit, every hour of radiation exposure and microgravity and isolation and circadian misalignment adds to the deficit. The crew gets weaker as the mission demands more. The margin between capability and requirement narrows as the most critical phase approaches. This is the dimension of the Mars return problem that engineering cannot fully address. You can build a better rocket. You can design a more reliable fuel plant. You can test your guidance systems 1,000 times on Earth. But you cannot prevent a human body from responding to 2.5 years of deep space exposure in the ways that biology dictates. You can mitigate the effects. You can slow them. You cannot eliminate them. And when you stack this biological reality on top of the engineering fragility described earlier, the picture that emerges is one of compound vulnerability. The hardware is degrading on one timeline. The crew is degrading on another. And the 2 timelines converge at the exact moment when both must perform at their best. The ascent vehicle has been on Mars for over 500 days. The crew has been away from Earth for over 700. The fuel was made by a system running for over a year. The transfer vehicle has been in orbit for over 2 years. Every component is at its oldest. Every system is at its most worn. Every person is at their most depleted. The food keeping them alive carries fewer nutrients than it did at the start. Their sleep has been disrupted for 16 months by a planetary rotation their bodies were never built for, and this is the moment when the chain must hold. What comes next is what happens when you lay these two timelines on top of each other and ask the question that no press conference has ever honestly answered. Given everything we know about what Mars does to machines and what deep space does to human beings, how close is the first human Mars mission to being a one-way trip, not by design, but by the weight of accumulated fragility that no amount of optimism can fully overcome? By now, you understand the chain. You understand the fuel that must be manufactured on an alien surface by machines that have never operated at scale. You understand the launch window that opens once every 26 months and does not care whether you are ready. You understand the ascent vehicle that must sit for 500 days in conditions that degrade every material and every circuit aboard it, and then perform flawlessly on its only ignition. You understand the orbital rendezvous, the trans-Earth injection, the months of deep space transit, and the atmospheric entry at Earth that demands precision from systems that have been aging for years. And you understand the crew, the bones that have been losing density since the day they left Earth, the muscles that are weaker, the hearts that have deconditioned, the kidneys that may be permanently altered, the eyes that may not see as clearly as they did at launch, the minds that have been isolated beyond any human experience in history, two timelines converging on a single moment, the hardware at its oldest, the crew at their most depleted, and the mission demanding more from both than it has at any point since departure. What happens when you lay these two realities on top of each other is not a single dramatic failure. It is something quieter and in many ways more unsettling. It is the recognition that the margin between a successful return and a permanent stay may be far thinner than any mission plan admits. Not because any one element is impossible, but because every element is conditional and the conditions stack against you with every passing day on Mars. Let us examine how this stacking works in practice. Consider a scenario that does not require any catastrophic failure. No explosion, no meteor strike, no dramatic Hollywood emergency, just the ordinary grinding accumulation of imperfection that any complex system experiences over time. The in-situ propellant plant lands on Mars during the precursor window, 26 months before the crew departs Earth. It begins producing methane and liquid oxygen from Martian carbon dioxide and subsurface water ice. The system is designed to produce the full propellant load with margin over approximately 450 days. In the first 100 days, it operates at 92% of its design capacity. 92% is a reasonable performance level for a first-of-its-kind industrial system operating autonomously on another planet. But it means the production timeline is already stretching. At day 180, a dust storm reduces solar input to the supplementary panels that support the nuclear power system's peak load capacity. The reactor continues operating, but the total available power drops below the threshold needed for full-rate production. The plant shifts to a reduced mode. It continues making propellant, but at 60% of design rate. The storm lasts 40 days. By the time it clears, the production schedule has slipped by roughly 3 weeks. At day 300, a seal in the water extraction system begins to degrade. The system does not fail. It leaks, slowly. The production rate drops by another 8% as less water feeds into the electrolysis stage. The crew, still months from departure on Earth, receives telemetry showing the decline. Engineers on Earth model the projections. The math is tight. The propellant load will be complete, but only if the system runs without further degradation for the remaining duration. The margin that was built into the schedule has been consumed. The crew launches from Earth. 7 months later, they arrive at Mars. The propellant plant has continued operating. The seal has degraded further, but the production is still active. The total load is at 87% of the target. The engineers calculate that the remaining production during the surface stay will close the gap if the system holds. 300 days into the surface stay, the seal fails completely. The water extraction rate drops to a level that cannot sustain methane production. The crew can repair the seal. They have the materials, but the repair takes 11 days, during which no propellant is produced. The schedule was already tight. Now it is behind. When the launch window opens, the propellant load is at 94% of the required amount. 94%. Not empty, not a catastrophic shortfall. 94%. The crew and mission control must now make a decision that no simulation has adequately prepared them for. Do they launch with a 6% deficit, knowing that the ascent trajectory and the trans-Earth injection have been calculated for a full load, and that 6% less delta V means a less optimal trajectory, a longer transit, and greater life support consumption? Or do they wait for the next window, 26 months later, and hope the propellant plant can make up the deficit while their supplies last? Neither option is safe. Neither option is clearly correct. And the decision must be made by a crew that has been away from Earth for over 2 years, whose bodies are weakened, whose cognitive performance has been eroded by radiation, isolation, and fatigue, and who are sitting on a planet that will kill them if any of the systems keeping them alive degrade faster than expected during an extended stay. This is not a dramatic catastrophe. This is the slow accumulation of imperfection. This is what real missions look like when they operate at the edge of capability for extended periods. No single failure causes the crisis. The crisis emerges from the interaction of a dozen partial failures, each one manageable in isolation, collectively pushing the mission toward a boundary it was never designed to cross. And this is the scenario where everything mostly works. Now, consider the current state of readiness for the technologies involved. As of the mid-2020s, the picture is sobering. No nation or company has landed a payload significantly exceeding 1 metric ton on the surface of Mars. The heaviest successful Mars landing was the Perseverance rover at approximately 1,025 kilograms. A crewed mission requires landing payloads in the range of tens to potentially over 100 metric tons. The entry, descent, and landing challenge for these masses in Mars's thin atmosphere is one of the most difficult unsolved problems in planetary engineering. NASA has studied it extensively. No solution has been flight demonstrated. No vehicle has ever launched from the surface of Mars. Not robotically. Not at any scale. The Mars sample return mission, which would have been the first demonstration, was effectively cancelled in early 2026 when Congress eliminated nearly all funding for future Mars missions. The technologies that would have been validated by that mission, precision landing, surface launch, orbital capture, sample transfer, and Earth return, remain undemonstrated. These are the same categories of technology required for a human return, scaled up by orders of magnitude. No full-scale ISRU propellant production system has been built, tested, or operated on Earth or on Mars. MOXIE demonstrated oxygen production at the scale of grams per hour. A human return mission requires production at the scale of kilograms per hour, sustained for months, integrated with water extraction, methane synthesis, cryogenic storage, and a power system that has never been deployed on the Martian surface. No nuclear fission reactor has operated on the surface of another planet. The kilopower concept has been tested on Earth in limited configurations. Flight qualification, launch, landing, deployment, and autonomous operation on Mars over a period of years remain entirely in the future. No human being has spent more than roughly 440 consecutive days in space. A Mars mission would require approximately 900. The health effects of that duration in deep space outside the magnetosphere, exposed to full galactic cosmic radiation, are projected from animal studies and models but have never been directly observed in humans. The 2024 kidney study and the broader body of research on radiation, bone loss, and cardiovascular deconditioning all point in the same direction. The effects are serious, cumulative, and in some cases potentially irreversible. But the complete picture of what 900 days does to a human body will not be known until someone endures it. No closed-loop life support system has operated autonomously for 3 years. The ISS life support system is impressive, but it receives regular resupply of consumables, replacement parts, and chemical cartridges from Earth. A Mars mission must carry or manufacture everything the life support system needs for the full duration, with no resupply. The reliability required is beyond anything that has been demonstrated in operational spaceflight. Each of these gaps is acknowledged by the engineering community. None of them is secret. They appear in NASA technical documents, in peer-reviewed papers, in independent assessments. They are discussed at conferences and in working groups. They are real, and they are large. What is less commonly acknowledged, at least in public, is what these gaps collectively mean for the return. Individually, each one is a problem to be solved. A difficult problem, yes. A problem that will require years of development and testing, yes. But solvable in principle. Collectively, they form something different. They form a picture of a return capability that does not yet exist in any meaningful sense, not as a demonstrated technology, not as a tested system, not as an integrating architecture that has been validated end-to-end. The return from Mars, as of right now, is a set of assumptions connected by arrows on a chart. Each arrow represents a technology gap. Each gap represents years of development, and the entire chart must come together simultaneously for the return to work. The public conversation about Mars obscures this reality by focusing on the elements that are closest to readiness. We can build big rockets. True, SpaceX has demonstrated the Starship launch vehicle at increasing levels of capability. We can get to Mars. Probably true. The transit itself, while long and radiation-heavy, uses propulsion technologies that exist and trajectories that are well understood. We can land on Mars. This is much harder than the public realizes, but it is a concentrated engineering challenge that focused investment could plausibly solve within a decade or two. We can come back from Mars. This is where the confidence should drop sharply, because the return depends on everything else working first. It depends on the landing delivering a functional ISRU plant. It depends on the ISRU plant producing enough propellant. It depends on the ascent vehicle surviving the surface stay. It depends on the crew being healthy enough to operate it. It depends on the transfer vehicle still functioning in orbit. It depends on the trajectory being achievable with the available fuel. It depends on the life support lasting another 9 months. It depends on the heat shield performing after years in space. The return is not a separate capability. It is the end product of every other capability functioning correctly in sequence over a period of years. It is the last link in the longest chain that human spaceflight has ever attempted. And if the first human Mars mission launches before every link in that chain has been independently verified, the crew will be betting their lives not on proven technology, but on the assumption that everything will work the first time in an environment that punishes assumptions. This is where the comparison to the moon breaks down entirely, and it is a comparison that is frequently invoked in public discussions of Mars. We went to the moon, the argument goes. Mars is harder, but we can do it. The underlying logic is that Apollo proved humanity can do audacious things when sufficiently motivated, and Mars is simply the next audacious thing. The comparison misses something fundamental. The moon is approximately 3 light seconds from Earth. Communication is nearly instantaneous. A crisis can be managed in real time by hundreds of engineers on the ground. The total mission duration of an Apollo flight was roughly 8 to 12 days. The crew launched in hardware that had been on Earth hours earlier. The ascent from the lunar surface used a vehicle that had been in the space environment for days, not years. The fuel was carried from Earth, not manufactured on the Moon. And if everything went wrong, as it did on Apollo 13, the crew was days from home. The entire return trajectory could be reshaped using the resources at hand. A Mars mission shares almost none of these characteristics. The communication delay removes real-time ground support. The mission duration is roughly 100 times longer than Apollo. The hardware must survive years, not days. The fuel must be made on site. And if everything goes wrong, the crew is months from home at best and potentially stranded with no viable return at worst. The Moon was an extraordinary achievement. It was audacious, dangerous, and inspiring, but it was a sprint. Mars is an ultramarathon. And the skills, the technologies, and the margins that carry you through a sprint do not automatically scale to an ultramarathon. The failure modes are different. The degradation profiles are different. The psychological demands are different. And the consequences of running out of margin are categorically different. On the Moon, running out of margin meant a few terrifying hours before the crew was home. On Mars, running out of margin means years of waiting with no guarantee of rescue, resupply, or survival. There is a pattern in the history of human exploration that is worth considering honestly. The first expeditions to reach extreme destinations often did not come back. The first serious attempts on Everest killed their climbers. The first expeditions to the South Pole were races against death, and one of the two teams did not survive the return. The first voyages across the Atlantic lost ships and crews to scurvy, storms, and navigation errors. In each case, the capability to reach the destination developed before the capability to return safely. The outbound journey was a problem of ambition and courage. The return was a problem of logistics, endurance, and margin, and the margin was almost always thinner than the explorers believed. Mars fits this pattern with uncomfortable precision. The ambition is real. The courage is available. The technology to reach Mars is within sight, if not yet within grasp. But the technology to return safely, to guarantee the return, to make the return something more than a best-case scenario dependent on hundreds of systems working correctly after years of degradation, that technology is further away than the public conversation suggests. And the gap between reaching Mars and returning from Mars is not a detail to be solved later. It is the central challenge of the entire enterprise. There is a term used in mission planning that captures this reality with clinical precision. It is called minimum mission success. It refers to the simplest definition of what constitutes an acceptable outcome. For a robotic Mars mission, minimum mission success might be landing intact and returning scientific data. For a sample return mission, it might be delivering even a single tube of Martian rock to a laboratory on Earth. For a crewed Mars mission, minimum mission success has always been defined as getting the crew home alive, not planting a flag, not collecting samples, not making history. Getting the crew home. Because if the crew does not come home, the mission is not a triumph, it is a tragedy. And no amount of scientific return or inspirational value changes that. This is the tension that sits at the heart of every serious Mars mission discussion behind closed doors. The people who plan these missions know the return is the hardest part. They know the technology gaps are real. They know the margins are thin. They know that launching a crew before the return chain is fully proven means accepting a level of risk that no government space agency has historically been willing to accept for a crewed mission. And yet the pressure to go is immense. National prestige, institutional momentum, public expectation, commercial ambition. the cultural weight of decades of Mars as the next frontier pushes relentlessly toward a launch date. And the return, because it is the least visible part of the mission, because it happens at the end, because it does not generate the inspiring images, risks being the element that receives the least scrutiny and the most optimism. The danger is not that someone will deliberately send a crew to Mars on a one-way mission. No responsible agency or organization would frame it that way. The danger is subtler. It is that the return will be treated as an engineering problem that will be solved in due course, that margins will be accepted as sufficient based on models rather than demonstrations, that the crew will launch with a return plan that is theoretically sound but operationally unproven, and that the gap between theory and reality will only become visible after the crew is on Mars, 200 million miles from help, staring at a propellant gauge that reads 94% and a launch window that is closing. The first humans on Mars will not be explorers in the way that word is commonly understood. They will be test subjects for every unproven link in the longest chain of dependent systems ever assembled. They will be testing the ISRU plant at full scale for the first time. They will be testing the ascent vehicle for the first time. They will be testing the long-duration life support system for the first time. They will be testing what 3 years of deep space radiation does to the human body for the first time. Every critical element of their return will be operating in uncharted territory. And they will be doing all of this knowing that if the test fails, there is no abort, there is no rescue, there is no early return. There is only Mars and the supplies they have left, and the next launch window 26 months away, and the hope that whatever broke can be fixed before the margins run out entirely. This is what Mars asks of its first crew. Not just courage, not just skill, not just endurance. It asks them to trust a chain that has never been tested whole, in an environment that has never been endured, at a distance that has never been crossed, with a return that has never been demonstrated. It asks them to be the proof that the chain holds. And it asks them to accept that if they are wrong, if the chain breaks at any point, they will be the ones who discover the failure, personally, permanently. The most unsettling truth about Mars is not that it is dangerous. Every frontier is dangerous. It is not that people might die there. People have died on every frontier humanity has ever crossed. The most unsettling truth is that humanity may be capable of sending people to Mars before it is capable of reliably bringing them home. That the technology of arrival may mature faster than the technology of return. That the ambition to reach Mars may outpace the patience to ensure the return works. And that the first human beings to stand on Martian soil may discover, through the slow accumulation of small failures and thinning margins, that the path home was never as solid as it appeared from Earth. Mars is close enough to dream about. It is visible in the night sky. We have photographs of its surface in extraordinary detail. We have driven robots across its plains and drilled into its rocks. We know what its sunsets look like. We know what its wind sounds like. It feels close. It feels like the next step. But closeness is an illusion created by images and ambition. The reality is a planet that is 7 months away on the fastest practical trajectory, reachable only during narrow windows separated by over 2 years, coated in toxic dust, bathed in radiation, devoid of breathable air, and offering a gravity field that may not be enough to keep a human body functional over the duration required for the return. Every beautiful photograph from the surface of Mars was taken by a machine that never needed to come home. The first humans will not have that luxury. They will stand on that surface and look up at a pale blue dot in the Martian sky, a dot that is Earth, that is home. And they will know that between them and that dot lies a chain of systems that must work, a body that must hold, a window that must open, and a margin that has been thinning since the day they left. And the question that will define their mission, the question that will define this entire chapter of human history, is not whether we were brave enough to send them. It is whether we were honest enough to make sure we could bring them back. As of today, that honesty is still catching up to the dream. And the distance between the two is measured not in miles, but in the quiet space between what we want to believe and what the engineering, the biology, and the physics actually say. Mars does not care about our timelines. It does not care about our ambitions. It does not care about our press conferences or our mission patches or the flags we plan to plant. Mars is a world governed by orbital mechanics and atmospheric chemistry and radiation flux, and it will treat the first human visitors with exactly the indifference it has shown to every rover, every lander, and every orbiter we have ever sent. The difference is that this time, someone will be there to feel it. And the hardest part of their journey will not be the landing that made the world cheer. It will be the long, quiet months that follow, when the window is still closed, the fuel is still being made, the body is still degrading, and home is a point of light in an alien sky that gets no closer until the chain is ready and every link holds. That is what Mars asks. That is what return demands. And until humanity can answer that demand with proven technology rather than projected confidence, the first footsteps on Mars will carry a weight that no one on Earth fully feels. The weight of a promise that has not yet been kept.